Okay, my goal today is to try and deal with that vector expression that had t's in it and try and interpret that realistically in geometric and visual terms. So let me start back in 2 dimensions. What do you need to make a line? If I ask you to graph a line, what do you need? 2 points. There's no reason not to do that in 3D. But once I have those 2 points, how do I make the line that goes through those 2 points? Well, that's our slope idea, right? But that quantizes the line. So this is actually a very weird question. How do I physically make the line from point 1 to point 2? It's a very strange sounding question. Give me the answer anyway on whatever you thought we were just thinking. I could take a vector, right, from one to the other. And then I could say, well, I want to take that vector and I want to keep going. And I also want to go the other way. So I could take a vector. From point 1 to point 2. And then I could say what I really need to do is I need to look at multiples of this vector. And if I were to take this and keep going in the positive direction, t, v, where t is a scalar, when t is positive, we get this vector to be bigger. And when t is negative, we get it to be the other direction. So I could actually get all of those if I looked at multiples of this vector v. There's just one problem, and it's really a technical problem. If I just look at multiples of a vector, what happens when t is 0? Right, with t is 0, I just get 0, right? And technically, if I were to think of this as vectors, the 0 vector is at the origin. But this line doesn't go through the origin, does it? I mean, I drew it just right, so it doesn't, but in general, this line might go through the origin, it might not. So somehow I have to take that into account. Now, in 2 dimensions, you started to give me, Ben, you started to give me the slope, change in y and change in x. But there's another piece to the line when we use slope, and what's the other piece? Some point, right? So I need a slope and I need a point. Well, I can think of this vector as being the slope, but I now need a point. And you say, oh, the line goes through here. Point from the origin to a point somewhere. Our intercept says go up the y-axis this far and start with that direction. So if I knew what this point was here on the y-axis, I could say, oh yeah, plus that point. But the only 2 points I know are point 1 and point 2. So I could build another vector. I could build a vector that goes from the origin to one of my points. And now I say, oh, I want the slope and the intercept. And so my equation for a line in terms of vectors, I could say, oh, my line is now the vector function. Start by going from 0 to this point. And then consider all the points that go in the direction of v, either in the positive direction or the negative direction. And now when t is 0, I'm at 0.1, aren't I? That's where this starts. That's my intercept, only it's not actually on one of the axes this time, right? Start here, and now go this way, wherever you want, positive or negative, any multiple of this vector. So I have a direction vector, v, and then I have a point to start from. Make sense? It's a different way of thinking about a line, because I don't have mx and b in the same way, right? But I have direction instead of slope, and point instead of intercept. Questions? Now, I wrote r of t. And the reason I wrote r is because I think of the vector as starting at the origin and working out. I think of that like a radius. It's pointing out some direction from the origin, no matter which way we're going. That's like a radius of a circle. So quite often you'll see this written as r0 for our vector going to a particular point. Go out to here, that's where we're going to start. Now go in this direction. Let's try one. I'll make my life easy. P1 is -1, 2. P2 is 1, 6. Okay. The vector v goes from point 1 to point 2. So in this case, my direction vector has what components? Right. Now I need this r0, my intercept vector, right? And I would let that go from the origin to either of these points. You want to do point 1 or point 2? Point 1? Well, then I'm taking this number, I'm subtracting 0, 0. Well, that really just means turn that into a vector. And now the equation for my line is r0 plus t v. You ready for the sneaky part? You've seen this before. I'm going to take this exact equation and make it one vector. I multiplied the t through on the 2, 4, and then I added the -1 and the 2 in the right places. That's the same equation, isn't it? You ready for how I know you've seen this before? That's really a set of parametric equations, isn't it? Here's how I move in the x direction. Here's how I move in the y direction. That's parametric equations, damn it. And the fact that they're both linear equations, helps you remember, this is a line. And if you eliminated the parameter, you could get y equals mx plus b, couldn't you? But I know the slope is 2. I go over 2, I go up 4. I know a point, I can derive this equation a lot of different ways. So I have a vector form of a line. I have the parametric equations for a line. Questions? Yeah, Cal 2 parametric. Pre-calc parametric. We did parametric equations in trig right at the end of trig, however many years ago that class was for you. But exactly the same way we did in chapter 10 last semester. Yeah, exactly the same way we did there. You ready for the amazing shift? Nothing about this entire process is restricted to 2D. Everything we did here works exactly the same in 3 dimensions until the very last step, because then I'm going to get x of t, y of t, and z of t. That's the only difference. So if I were to tell you to find the equation of the line through the points 2, 1, 5 and 3, 7, -2, -2, you could do exactly the same stuff. And find me a direction vector. And from that direction vector, find me the vector version of the line. It's literally the exact same process. What's my direction vector for this line? Wait a minute. 2, 1, 5. So that's up here. 3, 7, -2. So my line's going to go this way, from up here to down here. Going from up to down, my z should end up being negative in my direction vector. So if I let v be the vector p1, p2, I can't give components until I tell what it is. I get 1, 6, -7. And then, if I let R0 go to the first point, just like we did last time, I have R of t is 2, 1, 5 plus t, 1, 6, -7. And the corresponding parametric equations are found by gathering components. 2 plus t, 1 plus 6t, and 5 minus 7t. One degree of freedom, a one parameter family, linear people. And that's why it's linear. Whew. Questions. What happens when t equals 1? I get my other point, don't I? If I put in t equals 1, I'm going to get 3, 7, -2. Because I've gone 2.1 and then I've gone exactly the distance from P1 to P2. So plugging in 0 gets me my intercept. It gets me my starting point. And plugging in 1 gets me the other end of the direction vector. Which means if I were to say only use t going from 0 to 1, we wouldn't get the whole line. We'd get a segment. Question. Mia, do you see how this relates to the idea of having a vector with functions in it? The ones we had with cosine and sine were not going to be lines, but these are linear equations. My x of t, y of t, and z of t are all linear equations in t, so I end up with a straight line. So I have vector form of a line. I have parametric form of a line. I would like you to do me a favor with those parametric equations. I'd like you to take each of those parametric equations and solve for t. So the first one will give me t in terms of x. The second one will give me t in terms of y. And the third one will give me t in terms of z. T equals x minus 2. Now I'm going to be persnickety. I'm actually going to write that over 1 because that's the coefficient from my slope. Yes. And then from y, and from z,
z minus 5 or -7.
but all of those are t, aren't they? Which really means I know that all of those need to be equal to each other to satisfy this linear equation because they're all representations of the same t in one giant equation set. So I could write this. And notice my direction vector appears in the denominator, and my starting point, my intercept, appears in the numerator. 2, 1, negative, 2, 1, 5. Positive. These are called the symmetric equations for a line. Now, if it turns out that one of the direction vector numbers is 0, then when I go to do this part, I'll be dividing by 0, right? But that would mean that up here, that piece had no t's in it. And that just means x equals a number, or y equals a number, or z equals a number. And then I can ignore that part in the symmetric equations in general. Symmetric equations don't get used a lot in a regular calculus course. They show up in some very unusual places in physics, in chemistry, and in engineering texts. Because the idea of making things all look very similar, and that's what we got here, symmetric equations, is useful in a lot of cases. Questions? I have a line. Depending on which version of the equation you want to use, I almost always end up using the vector version or the parametric versions to do the work I'm most often doing. So we'll see those more than the symmetric equation. I can answer all sorts of questions from that. Let's take the line we came up with. Now, if we consider this in three-dimensional space with ourselves at the origin, this starts at a point in the first octant. Yes? And I said it was going down. The reason I said it was going down is this number is negative. But if it starts here in the first octant in front of us, then it's going to go through the floor somewhere. Where? Where does this line intersect the XY plane? Where does it intersect the YZ plane or the XZ plane? I can figure all that out, right? How? Which plane do you want to do first? Aha! If I'm on the XY plane, Z value is 0, I isolate Z. That really goes back to using the parametric versions. What T value is it when Z is 0? Which means you can give me now the X and the Y values that go with that, and you know where we went through the floor. And I'll just leave them as fractions, but now I know where that point is on the floor that we went through. If I want to know where we go through the YZ plane, what do I do? If I'm on this wall, X should be 0. If I want to know where we go through the XZ plane, then I need to set Y equal to 0. Question. Now, I said earlier that if we find the equation for the line, and then we said, oh, well, let T only go between 0 and 1, we have a line segment. But what if I haven't found the equation for the line yet? I would like an equation for the segment from point 1 to point 2. I'm going to call point 1 the start point and point 2 the end point. I'm just going to think about the line that we have in 3 dimensions in front of me. I'm going to say start here and go there from point 1 to point 2. So I'm going to say, well, what I really want is I want to blend parts of point 1 and parts of point 2. If I wanted to be exactly halfway between, I could say take the average of point 1 and point 2, right? If I wanted to be a third of the way, I could say, well, multiply by a third, multiply by 2/3. If I wanted to be 9/10 of the way, I could multiply by 9/10 and 1/10, right? It'd be more on this side and less on this side. So I can play this balancing game. Well, let's take some fraction of 0.1 and add the remaining fraction of 0.2. But I should do this in vectors. So instead of just writing 0.1 and 0.2, I'm going to write the vector from 0 to P1 and the vector from 0 to P2. And I always remember it as it's 1 minus t times the starting point, because then when t is 0, that's where I'm starting. And it's t times the ending point. If you were to do this for the 2 points we had earlier, you would end up with exactly the same equation that we already had for r of t. 215 plus t times 1, 6, negative 7. But you'd have to do a little more algebra to get it to look right. That's a useful shortcut to finding segments that we will use later in this course. So put a star on this. I didn't write down the page number for my edition of the book, but put a star on this formula. We're going to come back to it. Questions? Parallel lines have what's that word mean? Same slope. I don't have a slope in this case. I don't have a slope. I have a direction vector. So I want to say they have the same slope. I mean to say they have the same direction, right? So let me give you two lines. Let's let line 1 have direction 1 and intercept 1. And line 2, direction and intercept 2. So far, so good? Those are my slopes, quote unquote. They're really not slopes, but they're the right idea. And the reason I didn't want to use the word gradient is gradient has a very specific meaning we haven't gotten to yet. I promise we will, though. So I want those directions to match, right? How do I know if two vectors point in the same direction? They don't have to be exactly the same, point in the same direction, do they? Uh-oh. Because like 0, 1 points out the x-axis. I'm sorry, 1, 0, I, here's the right, I points out the x-axis, but so does 7, 0. So those go the same way. And technically, so does negative 2, 0. It still points along the x-axis. And since my line can take on any value for t, positive or negative, I don't necessarily just mean in one direction. I mean either parallel or anti-parallel. How do I know if two vectors point the same way?
Possible.
Not just similar. Or exactly opposite, right? Which means the only difference between these vectors and their unit vectors is a scalar, right? And that means the only difference between these two vectors will be a scalar. Vector 1 is parallel to vector 2 if and only if vector 1 is some multiple of vector 2. Where k is a non-zero scalar. So originally, the very first example I did, we had a line whose slope was 2. And the direction vector I came up with was 2, 4, right? But I could just as easily have used 1, 2, or 3, 6, or -4, -8. I still would have gotten the same line whose slope is, for your opinion, +2. Because I would have said go this way, or well, go that way. It's still the same direction. So this generalizes that idea. I don't have to have exactly the same slope. I just have to have a multiple. And the reason we had exactly the same slope in our old definition is because we took the ratio, right? We took change in y over change in x, basically reduced it to change in x is 1. But here I'm not saying that. I'm saying, well, for whatever x, you go up or down a certain amount of y and a certain amount of z. So now I need to know that those are still in proportion to one another. I'm really using the idea of similar triangles here. And this is our symbol for parallel. There was another thing we could do that wasn't parallel when we were doing lines back then in algebra. What was that one? I could use the slopes to tell me whether my lines were parallel or perpendicular. We already did perpendicular. Right, wait a minute, perpendicular. What do we know then? Right. But I am absolutely sure that that works in 2 dimensions. I'm going to mess with y'all. Ready? Line 1 starts at point 111 and goes in the direction of the x-axis. But it's up here. Line 2 starts at the origin and goes in the direction of the y-axis. Are these lines perpendicular? All right, here's where I get to ask a geometry question. The problem I have is that these lines don't touch. The first line goes in the direction of the x, but it's up here at the point 111. The second one goes in the direction of the y. It's down here at a height of 0. They don't meet. Are they perpendicular? Shouldn't matter in that case. They didn't touch each other. When we were talking about parallel lines never met. But we said all the other kinds of lines meet. Uh-oh. What happens here? These lines don't meet. So I need another term. We're going to call these skew lines. which means I'm going to reserve perpendicular for the idea that lines intersect. So back up here where we wrote V1 dot V2 equals 0, I'm also going to write and the lines have a point in common. So that's a sneaky little extra thing that we never needed to do in our previous classes because we're always working flat. And lines were either parallel or they had to cross somewhere. But now I have the ability to have lines that aren't parallel that don't ever cross. So I have this extra bit. So something I should check before I check the dot product is there a point in common? How would I check to see that two lines have a point in common? Now here's me being sneaky and giving you a hint right at the start. Normally I wrote my functions as functions of t. So over there on the left, I have x of t, y of t, z of t. And normally on the right, I would also have x of t, y of t, z of t. I changed the letter to an s. And I did this on purpose. Because in order for these two lines to actually cross, there has to be one value that makes all three of those equations true and all three of these equations true. A value for t and a value for s, which means I need to solve for two different things. I need to solve for t and s. How many equations do I need to solve for t and s? Uh-oh, I have three, but I really only need two equations and two variables, right? If I wanted to solve for this, I could ask, well, where do these two lines have the same x and y? Right? If I'm looking down from above, I'd see them cross somewhere. I know they're not parallel because the direction for this one is 1, 3, minus 1, and the direction for this one is 2, 1, 4. I know they're not parallel, but I don't know if they actually cross. So I can pick two of these equations and solve for the s and the t. See how I end up with two equations and two variables there? And now you can solve for t and s. I usually think it helps to rewrite the equations. Minus 2s plus t equals minus 1. Minus s plus 3t equals 5. I apologize in advance for ending up with an equation that has an s and a 5 in it at the same time, but that was not intentional. But now I can solve for s and t in dozens of different ways, right? Elimination, substitution, a 2x3 matrix, whatever you want to do at this point, we can solve. And I end up a little ways down the line with t equals 11 over 5 and s equals 8 over 5. And now I can ask, that's where the x's and the y's are the same. Is the z the same there? So what happens when you put that value of t into the z over there on the left? Or it would be 20 over 5 minus 11 over 5. I get 9 over 5. When I do S, it's -3 plus 4 times 8 over 5. That's 32 over 5 minus 15 over 5. 32 minus 15 is 17 over 5. So these lines don't actually cross, they're skewed. The first line is at a height of 9/5. The second line is a height of 17/5 at the point where we would expect them to cross each other. So when I look at it in 2D, they cross each other, but when I look at it in 3D, they don't.
So
I'm sorry?
they.
They cross at,
The.
I don't know what the X and the Y are for these T's, right? I'd have to go back and put that in to find out what X and Y were. I'd have to go back and put that in to find out what. But let's just do that, right? 1 plus 11 over 5 is 16 over 5. 2 times 8 over 5 is 16 over 5. -2, that's -22 over 5. I'm sorry, -10 over 5 plus 33 over 5. So that's 18 over 5. -10 and 30. No, I can do math. Really, I can't. -10 over 5, 33. That's 23 over 5. 3 would be 15 over 5 plus 8 over 5. That's 23. So the X and the Y that go with this. So if I look down from above, that's where I think they cross. But then I look from the side, I see this. Questions? I want to do planes. Here's my piece of cardboard. Problem. I can't use a direction vector the same way anymore. Because technically this plane goes in lots of different directions, doesn't it? If I think of the floor and I'm standing at a point, I could say go forward and I'll walk on the floor. Go to the right, go to the left, go behind, go at 30 degrees this way. I'm still on the floor, right? So the direction is a problem. And the easiest way to think about this is think of which direction we don't go. This plane can't go up. I can't walk on the floor by stepping up into thin air, can I? So the direction for a plane is not the direction in the plane, it's the direction out of the plane. And I don't want to just use any direction out of the plane. I want to use one that's guaranteed to be perpendicular to the plane. So instead of just using any direction vector, we're going to have a normal vector. So literally, I picture this pen taped to the surface of my plane, glued in place. And as my plane moves, I see that the direction vector sticks out from it at 90 degrees, no matter which way I'm going. Yes? No matter where I am on the plane. And I could do it up or I could do it down. It would still be perpendicular, wouldn't it? Okay. I need a crappy picture because even a bad picture helps. And I'm a bad artist. So I'm going to make a bad version of the picture in the book. Here's my plane. Here's a point on the plane P0. My normal vector sticks up, out at me. N. So I want to describe all of the points on this plane in terms of these two things. So what I'm going to do is I'm going to pick another point on this plane. Now, because I don't know what any of these numbers are, I'm going to call the point that I started at P0, X0, Y0, Z. I'm going to call my direction vector ABC. And I'm going to call this other random point XYZ. And the only thing I know at the moment is that this vector from P to P0, sorry, from P0 to P, that vector is in the plane. And if that vector is in the plane, what do I know about its relation to N? It's perpendicular. Hey, wait a minute. If two vectors are perpendicular, how do I determine that? The dot product is 0. Congratulations, you've given me an equation for a plane. That's the vector version of the equation for a plane. That doesn't look like. So hang on a second. Let's actually figure out what these vectors are. I said N was the vector ABC. And the vector from P to P0, sorry, from P0 to P is going to be N minus start. That's X minus X0, Y minus Y0, Z minus Z0. And that dot product should be 0. If I multiply that out, I get this. Now I'm going to multiply this out again. And I'm going to take all of the things that are just numbers, because I'll get AX, and then I'll get AX0. And then I'll get BY, and I'll get BY0. And I'll get CZ, and I'll get CZ0. But these are numbers, so let's just jam all that onto the other side. And then I just have a number, right? So it's AX, and BY, and CZ, and then some number over there. Now that looks like a plane to me, doesn't it? It looks like a line that we added one more dimension to. Hot damn. It worked. That's my plane equation. And this is called the scalar equation for the plane. So we have the vector equation, and now we have the scalar equation. The best part about the scalar equation is the normal vector is sitting right there, ABC. I get those numbers right away. I remembered the particular piece of cardboard that had the arrows on it that I needed last time. But if I had these vectors, or I had 3 points, and I wanted the plane, how could I get something that I know is perpendicular to those two vectors? I take the cross product of these two, and it sticks out. So if I have points, I can get two vectors. And if I have two vectors, I can get the cross product, I can get the direction vector. 3 points make a plane. And 3 points make the equations for my plane. Planes are parallel if their direction vectors are parallel. The angle between two planes is the same as the angle between their normal vectors. So they're perpendicular if that angle is 0. And I check that with the dot product. Those formulas that I mentioned about the distance between a line and a point, and the distance between a point and a plane, they're actually derived in this section, even though they were exercises in the last section. They're exactly going perpendicular. So we use the cross product to get those equations. Questions?
What do you mean the three variables for it to be a plane?
That would be the point here, X, Y, Z. That's our free thing. But the other way of thinking about it is that I have two free variables, direction 1 and direction 2, right? And then I do the cross product, and this cross product contains the information about both of those vectors, doesn't it? So I've hidden that other version. There is a way to do it in two variables. We'll do that later. I will see you all tomorrow. Have a wonderful rest of your day.